this video, we're going to define implicit differentiation and do some examples. So both of the two functions below give a relationship between x and y. The first function is explicitly solved for y. We see y equals x squared plus 8 sine x. So this is explicitly solved for y. The second function is in implicit form. So there's a relationship between x and y in this second function, but neither variable is explicitly solved for the other. So we're going to focus on equations that are written in this form in today's lecture. So we can find the derivative dy dx, or y prime in this case, using implicit differentiation. So the method for doing that is to do the following two steps. First, we take the derivative of both sides with respect to x, assuming that y is a function of x. And second, we solve for y prime. So we can write y prime like that. We can also write it as dy dx. It's often common to write it as dy dx instead because the primes can sort of be very small or get lost. So we'll have both y and y prime, or both y and dy dx as we're doing this derivative. So let's take a look at doing this for this function. 3 plus cosine of y equals e to the 3x. So first we'll take the derivative of both sides with respect to x, assuming y is a function of x. So taking the derivative now, the derivative of 3 is just 0. What's the derivative of cosine of y? So this is basically, when we're saying assuming y is a function of x, we're doing like a chain rule where what we have is, in this case, cosine of y, and y is our inside function, like with the chain rule, and cosine is our outside function. Here, derivative of cosine is negative sine of, leave the inside alone, y, and then we multiply by the derivative of the inside, and that's either y prime or dy dx. So we don't know what the derivative of y is with respect to x. That's what we're trying to solve for. We're just writing that as derivative of y is dy dx. We could also write that as y prime. Okay, continuing forward, now we're taking the derivative of the right-hand side, the derivative of e to the 3x. Well, again, we're using the chain rule there. We've got e to 3x is an inside function, so 3x is a function. So we've got derivative of e to the something is e to that something, multiplied by the derivative of the inside. Derivative of 3x is just 3. X is the independent variable, so we're taking the derivative of both sides with respect to x. Okay, so we have done the first step. We could simplify that slightly by just getting rid of the 0. We've got negative sine of y times dy dx equals 3e to the 3x. So that was step 1. Step 1 is accomplished. Now we can do step 2. We can solve for y prime, or solve for dy dx. We see that we've got negative sine y times dy dx. To get dy dx by itself, we can divide both sides by negative sine of y, and we'll have dy dx is equal to 3e to the 3x divided by negative sine of y, or dy dx is equal to negative 3e to the 3x over sine of y. So now we have the derivative of y with respect to x, and that derivative is in terms of both x and y. And that's okay, we are done. This is our solution. So as we saw above, implicit differentiation is an application of the chain rule. When we're taking the derivative with respect to x of cosine of y, again, we're treating like y as the inside function, cosine is the outside function. This is derivative of the outside, negative sine of, leave the inside alone, multiply by the derivative of the inside, dy dx. And when you're doing implicit differentiation, anytime you see a y, you are going to be somehow getting a dy dx out of that. The other comment is, again, This solution is written in terms of both y and x. In terms of y and x. And again, that is okay. That is not a problem. That's what we expect in implicit differentiation. All right, let's do some more examples using implicit differentiation to find the derivative of y in the following equations. So the derivative of y prime, is the same as dy dx. We've also seen f of x equals y. So these are all different notations. We could also write derivative of f of x with respect to x is another option. But this is what we're looking to find. So let's do that for 2y cubed plus 3x to the fifth equals e to the 4y. So that's first problem. Second, x plus y to the fifth equals 2 times y squared minus 4. And third, 2 tangent of y equals 2e to the x minus 5e to the 3y. So grab a pencil and paper, pause, try these out, and we'll talk about them together. Okay, so first problem. So we've got 2y cubed plus 3x to the fifth equals e to the 4y. So we're going to start by taking the derivative of both sides with respect to x, assuming that y is a function of x. So when we take the derivative of 2y cubed, that's the outside function is 2 times something to the third power. So 2 times something to the third power, 3, leave the inside function y alone, subtract 1 from the exponent. So we've done the derivative of the outside, and then we multiply by the derivative of the inside function, which is y, a function of x, and that's dy dx. So that's the derivative of 2y cubed plus the derivative of 3x to the fifth. We can just take this normally because we're assuming that everything is a function of x. So this would just be 15x to the fourth, like normal, equals derivative of e to the 4y. Again, now this 4y is the inside function, and the outside function is e to the something. Derivative of e to the something is e to that same thing, multiplied by the derivative of the inside. The derivative of 4y is 4, we're using the constant multiple rule, times the derivative of y is dy dx. Okay, so now we've taken the derivative. If we want, we could simplify that slightly. 6y squared dy dx plus 15x to the fourth equals 4e to the 4y dy dx. And now our next step, so this is the derivative. We've taken the derivative, and now we want to solve for dy dx. Solve for the derivative. So we want to get all the dy dx's on one side. So all dy dx on one side is our next goal. So right now we've got a dy dx term over here and a dy dx term over here. This one's by itself, so let's subtract this over to the other side. So we have 15x to the fourth is equal to 4e to the 4y dy dx minus 6y squared dy dx. And our next step to solve for dy dx could be to factor out dy dx. So we could factor dy dx out of the terms on the right-hand side. We'd have 15x to the fourth equals, so the first dy dx is multiplied by e to the 4y. The second is multiplied by negative 6y squared. So that is multiplied by dy dx. And now our last step in solving for dy dx would be to divide by the multiple of dy dx. So we can divide both sides by that 4e to the 4y minus 6y squared, and we'll have 15x to the fourth divided by 4e to the 4y minus 6y squared is equal to dy dx. And now we have the derivative of y with respect to x in terms of both x to y and y. The derivative is 15x to the fourth divided by 4e to the 4y minus 6y squared. So I would encourage you, especially if you had trouble with that one, to again pause the video now that you've seen another one done all the way through, and try or look back at examples 2 and 3, try them again or make sure you did them correctly before moving on to look at my solutions for the next two. Okay, so x plus y to the fifth power equals 2y squared minus 4. Again, we're going to take the derivative of both sides with respect to x, assuming y is a function of x. So the derivative of x plus y to the fifth, we're using a chain rule there, and that is 5 times, leave the inside alone, x plus y to the fourth power. Now we need to multiply by the derivative of the inside. Derivative of x with respect to x is just 1, plus derivative of y with respect to x is dy dx. Now this is equal to, on the other side, derivative of 2y squared, using the power rule and the chain rule. That's 2 times 2 is 4, y to the 1 power, times the derivative of y, the derivative of the inside is dy dx, minus derivative of 4 is just 0. And so we're going to need to get dy dx by itself. And so to be able to get dy dx by itself, we need to multiply this term and this term times the previous so that we can get the dy dx terms separated from the non-dy dx terms. So we're going to say this is equal to 5x plus y to the fourth times 1. That's just 5x plus y to the fourth, plus 5x plus y to the fourth times dy dx. That's 5x plus y to the fourth times dy dx is equal to 4y dy dx. And again, I need to get all my dy dx terms on one side of the equation so that I can factor out. So I'm going to get dy dx terms on one side. And so I'm going to subtract this term over to give 5 times x plus y to the fourth power equals 4y dy dx minus 5x plus y to the fourth power dy dx. And so now I'm going to factor out dy dx, factor out dy dx on the right, and that will give me 5 times x plus y to the fourth power equals 4y is the first term that's multiplied by dy dx, minus 5 times x plus y to the fourth power, and each of those terms are multiplied by dy dx. And now, last step, I can divide by the multiple of dy dx, and so that will give me 5x plus y to the fourth power, all divided by the multiple of dy dx, so divided by 4y minus 5x plus y to the fourth power, and that is equal to dy dx. So that is my solution. All right, last problem. We've got 2 tangent of y equals 2e to the x minus 5e to the y. So taking derivative of both sides with respect to x, derivative of 2 tangent of y is 2 secant squared of y multiplied by the derivative of the inside multiplied by dy dx. And that's the derivative of the left-hand side. That's equal to derivative of 2e to the x is just 2 times the derivative of e to the x, which is just itself, minus 5 times e to the 3y. The derivative of that is 5, constant multiple rule, times the derivative of e to the 3y. This is a chain rule with 3y being the inside function. So take the derivative of the outside function, leave the inside alone, multiply by the derivative of the inside. Derivative of the inside is, derivative of 3y is 3 dy dx. One thing to note here, what's the difference between like what's going on here and what's going on there? Here, well, first of all, there's not a 3, but also we didn't need to multiply by dx. And just note that that's because, if we did think of the derivative with respect to x of e to the x or 2e to the x as 2e to the x times the derivative of the inside derivative of x with respect to x, well, that's just 1. That's just 2 times e to the x. The derivative of x with respect to itself is just 1, so that would just be 2e to the x. So we could think of like using implicit differentiation all the time. It's just that anytime we took the derivative of e to the x with respect to itself, we would get 1, and so, that simplifies to this. Okay, now we're going to get the dy dx's on one side. So I've got this dy dx term and this dy dx term. These entire things are dy dx terms because they are all multiplied together. They're not separated by pluses or minus. If everything is multiplied without any pluses or minuses in between, that is one single term. So let's now subtract this, or I guess we're going to add this over to the other side to get rid of it on the right-hand side. We'll have 2 secant squared of y dy dx plus 5e to the 3y times 3 dy dx. 3 times y is 15. So dy dx is equal to 2e to the x. Now, again, we're going to factor the dy dx terms out of the left-hand side. And so we'll have 2 secant squared y plus 15e to the 3y multiplied by dy dx is equal to 2e to the x. And last step, divide both sides by the multiple of dy dx. dy dx is equal to 2e to the x divided by 2 secant squared y plus 15e to the 3y. And that is our solution.